So the aldol reaction is an important one in our discussion of alpha carbon reactions. This aldol is ran in base, so the first thing we do is pluck an alpha hydrogen from our aldehyde. Do we have to draw out all the carbons and hydrogens? No, but I think it's helpful the first time you see an aldol at least. So we plucked an alpha hydrogen and made an enolate. This is an enolate. Remember, it's the carbanion version of the enolate. That enolate can attack lots of things. In an aldol, it's always going to attack a carbonyl. Well, this reaction has many carbonyls in solution. All of these that you started with, this is acetaldehyde, remember 2-carbon aldehyde, acetaldehyde. When you use a base like hydroxide, does hydroxide quantitatively deprotonate to make this enolate? No way. Acetaldehyde, some of it turns into enolate, but there's a lot of acetaldehyde left over that has not been converted to enolate. So your enolate attacks the carbonyl carbon of another acetaldehyde molecule. Lots of color coding on this one. Our original acetaldehyde is here in black. Our new bond here in red. And our acetaldehyde that got attacked here in blue. Hydroxide is the base you chose, so water may be your solvent. So we're going to use water as the proton source to protonate our O-. And we get this guy. This thing that I'm drawing now is officially an aldol product. An aldol is an aldehyde and an alcohol product. Aldol. Drawing it in the zigzaggy way without all the hydrogens and stuff shown, all the carbons and hydrogens shown. We've got this. A beta hydroxy aldehyde. Aldol. Aldehyde and alcohol in the same molecule. The next slide says, on occasion, aldols dehydrate. So I'm going to take our aldol product here, but I'm going to go back to the all carbon and hydrogen version. And I'm going to say, what if we cook it in hydroxide? The first thing that happens is you pluck an alpha hydrogen. The alpha hydrogen is more acidic than a typical alkane hydrogen. So you make a second enolate here. Still trying to keep my color coding consistent. Switching a lot of pens over here. So I have this, which is another enolate. And that enolate folds down and kicks out hydroxide. But wait, hydroxide is a terrible, horrible, no good, very bad leaving group. Well, usually that's true. But this whole thing is being cooked in hydroxide. So hydroxide's an okay leaving group at this stage. So I have my original acetaldehyde, a new pi bond, and then my blue acetaldehyde, I've lost the oxygen from it. I have a little bit more to say about the reaction overall, but before I get too far, this last step of dehydration in base, this last step makes an alkene. So maybe you would want to call it an elimination reaction, an E. But is it an E1? No, because E1 has to go through a carbocation. Is it E2? No, because E2 is concerted all in one step. Here, you take a hydrogen and make this, then you fold down and kick out. This reaction step is called E1CB, elimination unimolecular via the conjugate base. So your first step is acid base to make a conjugate base. That's this enol, a conjugate base. That conjugate base then folds down and kicks out your leaving group to do your elimination. E1CB. When you do an aldol in base, you do E1CB. So if we take a quick look overall, what has happened throughout the course of this reaction? Well, you lose a water molecule. You lose one H and nope. You lose a water molecule. You lose two H's and one O in the overall dehydration process. And the alpha carbon of your original carbonyl becomes connected to the carbon that was another carbonyl. You lose water and you connect this carbon to that carbon. This is often called the aldol condensation product. So on occasion, aldols dehydrate. The first one is an aldol addition, make a beta hydroxyaldehyde. The second bit is an aldol condensation. A condensation reaction is a reaction that loses a small molecule product. Water is the official molecule here that's lost. That's aldol. It's an important one. A couple of notes about aldol before we run through another example. The product is either a beta hydroxyaldehyde or an alpha beta unsaturated aldehyde. So the beta hydroxyaldehyde, that's the product of aldol addition. Alpha beta unsaturated, that's the product of aldol condensation. The reaction is reversible, so you could draw the condensation product breaking back down into two carbonyl compounds. Aldehydes are more reactive than ketones, so aldehydes are better at doing this type of reaction, but a ketone can do this type of reaction, and we will see some do it. We drew the mechanism as an aldol reaction with hydroxide as the base, so an enolate was the nucleophile that we saw. But if you ran this thing in acid, you can still get aldol to take place in acid. It's just that your nucleophile is an enol. And in acid, you always dehydrate via an E1 mechanism because carbocations are stable in acid. All right, let's do this fancy thing called a crossed aldol. All right, in this crossed aldol, we're going to do some color coding, but a little bit different color coding than we did previously. We're going to have a blue aldehyde and a pink aldehyde. We're not going to walk through the whole mechanism, but we're going to talk through how this thing could work, or really how this thing does work. We're going to do it in sodium hydroxide, just like the last one. Does this blue aldehyde have alpha hydrogens? Uh-huh. So can it become an enolate? Uh-huh. So we're going to get some blue enolate forming. Does the pink aldehyde have alpha hydrogens? Uh-huh. So can it form an enolate? Uh-huh. So we've got two different types of enolates, blue enolate and pink enolate. When you have a blue enolate, can it attack a blue aldehyde? Because is there plenty of blue aldehyde in solution? Yep. When you have a blue enolate, can it attack a pink aldehyde? Because there's plenty of pink aldehyde in solution? Uh-huh. So if I have blue enolate attacking blue aldehyde, I get that product. If I have blue enolate attacking pink aldehyde, I get this product as my beta hydroxyaldehydes. That's if blue is the enolate. What if pink is the enolate? Pink can attack pink to get me this product. Pink can attack blue to get me this product. So this crossed aldol creates 4 beta hydroxy ketones, 4 beta hydroxyaldehydes, because both of them had alpha hydrogens, so both of them can form enolates, and both of them can be attacked by an enolate. If I then consider dehydration of these four molecules, that blue on blue dehydrates to this. But wait, there's another thing that we didn't mention when we talked about aldol just a moment ago. Would you call this alkene E or Z? Oh man. Aldol can create E and Z products upon dehydration. So our one blue on blue beta hydroxyaldehyde became two alpha beta unsaturated aldehydes. Oh man, isn't that painful? The blue on pink version looks like this. Slash like this. One is E, one is Z. I hope you know who's who. The pink on pink. And the pink on blue. So this crossed aldol creates 8 potential dehydrated aldol condensation products. Huh, that's a mess, right? It's very helpful to control a crossed aldol sometimes. And there are 3 main methods to do that. Let's talk through those 3 main methods. Method number 1 says, react an aldehyde which has no alpha hydrogen with a ketone which has only one type of alpha hydrogen. Let's make something up. React an aldehyde which has no alpha hydrogen with a ketone which has one type of alpha hydrogen. So this has 2 sets of alpha hydrogens, but because this molecule is symmetric, this side and that side alpha hydrogen are the same. So who's capable of making an enolate? Only the ketone. So we're going to get the ketone turning into an enolate, like so, if we did this in hydroxide, we'll say. And then what's more reactive, aldehyde or ketone? Aldehyde, hopefully you said that. Aldehyde's more reactive than ketone, so the aldehyde gets attacked. And we end up with this aldol addition product, which can then dehydrate to this aldol condensation product. That is an E or Z thing. An E and Z and aldols is commonly a thing, but we're going to kind of ignore that. This could be E and Z, but we've drawn it as only E. Method number 2 to help control a crossed aldol says, place an aldehyde with no alpha hydrogens. Okay, let's make it up. Aldehyde with no alpha hydrogens in base, and slowly add an aldehyde that has alpha hydrogens. So an aldehyde that has no alpha hydrogens in base, and slowly add an aldehyde that does have alpha hydrogens. Who's going to become the enolate? The aldehyde that does have alpha hydrogens. Okay, then why are you slowly adding it? Well, you're hoping or planning that there's never an appreciable amount of this aldehyde in solution. You want that aldehyde to drip into solution and become deprotonated soon after it gets into solution, because if you do that, it ensures that this becomes aldehyde and this is the thing that gets attacked. So we're not drawing mechanisms here. This is the aldol addition product. This is the E version of the aldol condensation product. We're not worried about E or Z. It is a thing, but we're not worried about it. And finally, to be conservative, method number 3 says LDA. What does that matter? This is the most flexible method. We introduced LDA in the last video. Hopefully it's familiar to you. LDA quantitatively deprotonates things. So we could do something like this aldehyde plus LDA, and then add even a ketone, which is not traditionally easy to attack in an aldol. This plus LDA ensures that after step 1, you have this and only this in solution. You have absolutely no propionaldehyde that is left over. All of it has been converted to enolate. So then that enolate attacks the ketone or whatever thing that you add next. So that ketone becomes that. That's the beta hydroxyaldehyde version. The dehydrated version. Ta-da! Isn't it nice that that one does not have E and Z? Crossed aldols, you need to know how to predict the products of them, but they can also get a little confusing because they make so many products. You need to know how to control them as well. The next slide just says predict the product, but we're going to go further than that. We're going to draw a mechanism. But before we are able to draw a mechanism, we have to figure out what the heck should be happening in this reaction. This is TSOH, tosic acid. It's an acid like sulfuric. It's just soluble in organic solvents. So am I going to pluck an alpha hydrogen and make an enolate? No. I'm going to make an enol, and that enol will attack a carbonyl. But I have 2 carbonyls. So which one's going to become an enol and which one's going to attack what? Oh boy. Even when an enol is acting as the nucleophile, it's the alpha carbon that is the nucleophilic atom. So if this alpha carbon was your nucleophile, it could attack that carbonyl. If this alpha carbon were the nucleophile, it could attack that carbonyl. And it would close up and make a ring that's 1, 2, 3, 4, 5, 6 carbons big. Let me actually put letters on here so that I can refer to those a few times. So carbon A would attack carbon F, and it would make a 6 ring. If carbon C were my nucleophilic carbon instead, carbon C could attack carbon F, and it would make a 4-membered ring. That's not the greatest. 6 sounds much better. If carbon E were my nucleophilic enolate enol carbon, carbon E could attack B, and if that happened, we would get a 4-membered ring. I don't love it. Hopefully you neither. If carbon G were my nucleophilic carbon, carbon G could attack carbon B, and I would get a 6-membered ring. So A attacking F or G attacking B sounds best. If you want to try to construct A attacking F, you end up with something a little bit wonky. That might be too many carbons. Yep, it is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. You get a bicyclic kind of thing like this. Do bicyclic things exist? Absolutely. But would we make something wonky like that when some other option is available? Nah. Let's have G attack B. So all of that discussion was to say what attacks what. Now it's time to draw a mechanism. Yep. So I'm going to do something that I will allow you to do as well. This is an acid, so the first step is turn this FG thing into an enol, because it's the enol that behaves as the nucleophile, not an enolate. Are you responsible for knowing a tautomerization mechanism? Yes, and you're going to have to draw some in your online homework stuff, but we're going to avoid drawing that right now to just give me this enol. When you're in acid, it's common, as we have seen previously, to protonate the carbonyl oxygen before you attack it. So let's do that. And then everything is poised and ready to go. Attack the carbonyl carbon. I'm going to do one more step and fold down electrons like that while I attack. What that results in is carbon G becoming connected to carbon B. You should go through and count and make sure you understand why this happens this way. But carbon G is this one, G, and it attacked carbon B. We'll put those other letters on there in red for good measure. Carbon F should have a doubly bonded oxygen with a hydrogen still on it. Carbon B should have an OH. Some base in solution. Let's clean up this positively charged thing first to get me here. This is my beta hydroxy aldehyde, except it's a ketone. This is a typical aldol product. However, when you run an aldol in acid, it should always dehydrate. So we're going to use some more of our tosic acid. Protonate my OH to make a better leaving group, because in acid you need it to be protonated before it leaves. And then let it go, let it go. Can't hold it back anymore. You're welcome. To get me a carbocation, looking like E1 here. Some base in solution. Takes another alpha hydrogen and folds in electrons to make this thing. What is this thing? This thing is an alpha, beta, unsaturated ketone. It's the aldol condensation product. Magic. We will do one more quick predict the product together. And then you're going to have to do some on your own. I hope that you see two carbonyls in the same molecule and you say, uh-oh, this thing gonna make a ring. It's gonna close up and make a ring. But you have to figure out what size ring should it make. This one is in base, so we have to consider a couple of things. Which carbon numbers could be enolates? Carbon 1, carbon 3, and carbon 7 could all be enolates. If carbon 1 is an enolate, it's going to attack carbonyl 8. If carbon 3 is an enolate, it's also going to attack carbonyl 8. If carbon 7 is an enolate, it's going to attack carbonyl number 2. 1 attacking 8, 8-membered ring, no good. 3 attacking 8, that's a 6-membered ring, that's better. 7 attacking 2, uh-oh, that's also a 6-membered ring. 1 is better than the other. But, 1 is better than the other. This is a ketone. This is an aldehyde. Are those things created equally? Are those electrophiles created equally? Who's the better electrophile? The aldehyde. So who should get attacked? The aldehyde. So we're going to make carbon number 3 into the enolate, and we're going to make it attack carbon number 8. Not walking through all of the mechanistic details, we're going to have this enolate. It's going to attack this carbonyl. We get a 6-membered ring. I probably should have been consistent with my numbering from before. Let's do that. Carbon number 3 and carbon number 8 get connected. I did not specify where those things were. I just slapped some numbers on my 6-membered ring. If carbon number 3 attacks number 8 should have an O- on it. Number 3 should have carbon number 2 and carbon number 1 connected. And carbon number 2 should have a carbonyl. You have to protonate to get your beta hydroxyaldehyde, beta hydroxy ketone thing. So you get this. This is and should be your appropriate predicted product. Because it's not ran in acid, it does not count. You should not predict it dehydrated. However, if you put a little heat on it from the beginning, heat promotes dehydration. Heat promotes elimination. So if this reaction were heated, then you should predict this as the product. But that's if and only if it's heated. So you'll know from the beginning, sodium hydroxide in heat means dehydrate. Acid means dehydrate. And there's one more thing that means dehydrate. If you can make a super conjugated system, you should dehydrate. What is the official definition of super conjugated? You're probably going to need at least 6 pi electrons in the conjugated system in the end to promote dehydration. We'll see a lot of examples, so hopefully you'll figure out what I mean by that exactly. The 4 examples in the next couple of slides you should work on your own. You should predict the appropriate products and determine whether that should be the beta hydroxyaldehyde product or the alpha beta unsaturated product, as in, does it dehydrate or not? Good luck. So as you may imagine, aldols are common targets of synthesis. So if you're being told to synthesize something and you recognize that it's a beta hydroxyaldehyde or ketone, beta hydroxycarbonyl, you want to do an aldol. Remember, aldol always makes a bond between the alpha carbon and the beta carbon, and it's specifically the alpha and the beta that has the OH on it if it's a beta hydroxy. If you recognize that it's an unsaturated compound, alpha beta unsaturated, you're breaking the bond between the alpha and the beta. Again, aldol makes alpha beta bonds. It makes carbon-carbon bonds, alpha beta carbon-carbon bonds. The carbon that is the beta in the target molecule used to be a carbonyl carbon. Yeah? Yeah. Can you look at this giant molecule and detect that it's an aldol product? I hope so. Good luck.